Lesson 15, Mean. The mean, or more precisely, the arithmetic mean, is a measure of central tendency, or average, of the data. The mean measures central tendency by finding the center of gravity, or balancing point, of the data. To illustrate this idea, imagine all the data values on a number line. The mean is that precise point for which all the data values balance out. The mean is calculated by summing all of the data values and dividing that sum by the total number of data values. The population mean is given by the formula mu sub x is equal to the sum of all the population values divided by the population size, capital N. The sample mean is given by the formula x bar is equal to the sum of all the sample data values divided by the sample size, lowercase n. The population mean is denoted by the Greek letter mu. Subscripts provide clarification. Here, it's denoted as mu sub capital X, denoting that this is the mean for the population of all the data values. But if the data was grade point averages, we could denote it as mu sub GPA for the population mean of all grade point averages. The sample mean of the data values x is denoted by the symbol x bar. Both the population mean mu and the sample mean x bar are calculated in the very same way. That is, you have to sum up all the data values and divide by the total number of data values that were added. The only difference is the context. That is, are the data values that we're summing up all the data values in the entire population? If so, then we're calculating the population mean. But if the data values are only part of the population, that is, a sample, then we're calculating the sample mean. This notation here, using the summation notation in mathematics, denotes the summation of all the population values. And this sum is divided by the population size, capital N, to calculate the population mean, mu. Here, the same summation notation is used to denote the summation of all the sample values, and this sum is divided by the sample size, lowercase n, to calculate the sample mean, x bar. Now that we've calculated the mean for this data, we then need to interpret the result. Interpretation is different from a description. Descriptions just merely report the results that can be directly derived from the data. For instance, the description of this result could be that the mean Unit 1 examination score for this student is 3. An interpretation gives meaning to this result. That is, it tries to explain what this result is telling us. So since the mean is calculating the center of gravity, or the balancing point for the data, the interpretation must give this meaning. So here, the balancing point of this student's Unit 1 examination scores is 3, would be the interpretation. Now, to illustrate this idea, we could take all the Unit 1 examination scores that the student had and put them on a number line. Now, the mean is that precise point at which all the data balances. Now, the mean finds the balancing point, or center of gravity, by balancing out all the deviations that the data values are from this mean. So, for instance, the score of 3 that the student earned on one of their problems is precisely at the mean. So the data score of 3 is 0 points away from the mean, because 3 actually equals the mean. But the 2 scores on the problems where the student scored a 4 are each 1 point above the mean score of 3. The problem where the student scored a 2 deviates 1 point below the mean of 3. The score of 5 deviates 2 points above the mean. And the score on the test where the student earned a 0, 0 is 3 points below the mean. So here what the mean does is find the point where all these deviations of the data values from the mean balance out. If you look at the deviations below the mean, we have -1, -3, or a total of -4 points below the mean. And if we look at the deviations of the scores above the mean, we have +1, +1, and +2, which gives plus 4 points above the mean. Now the minus 4 points below the mean and the plus 4 points above the mean cancel out. That is, the data is all balanced or zeroes out precisely at the mean of 3. One consequence of the mean being the balancing point of the data is the mean is affected by extreme data values. To illustrate this, here we can look at some data that is balanced at the mean. But if the minimum data value was extremely small, that is, way far below all the rest of the other data values, the mean would have to compensate for this to keep everything in balance. Also, if the maximum data value was extremely large, that is, it deviated much farther than all the other data values, the mean would have to compensate for this much bigger data value to keep everything in balance. The mean must adjust for extreme data values to maintain the balance. Thus, the mean could produce distorted results whenever the data values include what statisticians call outliers. That is, extremely small or extremely large data values that deviate tremendously from the other population or sample values. So, as long as outliers are not present in the data, the mean is the preferred method for measuring central tendency.